All right, next up is Michael Koval, presenting work that's been done at Carnegie Mellon.
Thank you for the introduction. Like Ken said, I'm presenting work done jointly with my advisors, Sid Srinivasa and Nancy Pollard at CMU. This is done jointly in collaboration with David Su at the National University of Singapore. Our goal is to get robots to reliably manipulate objects in uncertain and cluttered environments. So here's an example of a sort of the type of non-prehensile manipulation action we'd like to generate autonomously and robustly. And like you see here, sometimes sort of traditional techniques that don't consider uncertainty work well. But as any of us who have worked on a real robot know, there are plenty of exciting things that can go wrong. And our goal of this talk is really to try to close the gap between this performance and the performance you saw in the previous video in a principled way. And the root cause of these failures is all fundamentally the same reason, that there's a mismatch between the perceived environment, what the robot thinks the environment looks like, and what it actually does. And this comes from numerous sources of uncertainty, everything from perceptual uncertainty to controller error to proprioceptive uncertainty. In this talk, I'm going to specifically focus on perceptual uncertainty and even more specifically talk about how we can use contact sensing to reliably manipulate objects under uncertainty. And contact sensing is interesting for a few reasons. First, it's sort of intimately linked with manipulation. We manipulate objects by applying forces to them. We need contact to impart forces. Second, from an algorithmic perspective, it's very interesting because contact sensors frequently require active sensing. Here's an example where the robot only has sensors on its fingertips, shown in red. It has a large amount of pose uncertainty, shown as a bunch of hypotheses over object pose. And to grasp it, it has to actually take this information gathering action to force it into contact with the fingertip so it can localize it. So our goal is to generate this type of plan autonomously. And the formulation, the framework we use to do this is a partially observable Markov decision process, a POMDP. And just to formalize the notation a bit, we plan in a state space that consists of the robot configuration, so 7 joint angles for Herb's right arm, an object pose, and I'll specifically talk about the case where we're doing planar manipulation with a quasi-static pushing model, so we don't need velocities in the state. An action is a full joint space trajectory, so a C of t of the robot's 7 joints in this case, and we have some sort of stochastic transition model for how the object moves when we push it. We additionally have a stochastic observation model about how we get feedback from binary contact sensors after taking each action. And we will assume that we have perfect proprioception, so we know what the robot's own joint angles are, for example, through encoders. And in the past, we've successfully used this type of POMDP framework to generate the type of information gathering action I showed you before. Here's an example from an IJRR paper last year, where the robot, just given the fact that it needs to center the bottle in the hand, does synthesize this action where it forces into contact with the fingertip. However, sort of the dirty laundry here, using the wafer term, is that we did this without considering kinematic constraints. So if you execute this in a more cluttered environment, or for example, even on this empty table, if you move the bottle slightly to the right, the robot's not aware that its elbow will hit the table, and while executing that information gathering action, it fails due to environment collision. And like I hinted at, the reason this occurs is because the robot's configuration space is this high-dimensional, continuous, nasty space that we really don't want to plan in. So instead, we project this down to just the pose of an object relative to the hand. And this is just this nice 3-dimensional space that lives in SE2. And this is mostly true if you're not near any obstacles. This is a great model. We can just consider the object evolving as we push it relative to the hand. But the place where it fails is really when you introduce kinematic constraints that depend on the full robot configuration. In this case, an obstacle, or perhaps a joint limit or a self-collision. And there's no way we can project this, this obstacle from this high-dimensional space into this low-dimensional space. It fundamentally depends on the joint configuration. So really the topic of this talk is how do we use contact sensing to be robust in the presence of many kinematic constraints. And the key insight that we use on a few different fronts is that we can still exploit this hand relative structure, but instead of using it as a hard constraint that our policy must follow this form, we'll use it as a heuristic to guide a search in the full joint robot object configuration space. And that heuristic will give us tractability. And the way we do this is using something we call an action template. So the idea is we're going to simultaneously track the robot state of the environment in this joint robot object configuration space. This is this 10-dimensional space in this case. But we can project any of those configurations down into this hand relative space that only lives in SE3. And we'll be careful to define all of our actions, or as I'm calling them now, action templates in this hand relative space. So this is defined purely in terms of a relative translation and rotation of the hand. And given an action template and given an initial configuration, we can use motion planning, for example, a constrained motion planner, to instantiate this motion on the full joint space. And this gives us the power to predict offline while we're planning what the outcome of an action is in the full joint robot object configuration space before we execute it, before we hit anything in the real world. And if you think about what these action templates look like, if you tessellate them, you get a lattice in configuration space that is very similar to the type of state space lattice you'll see in a search-based planning community and mobile robot planning, where we have nodes that represent configurations and edges that represent trajectories between configurations. And the nice thing about this formulation is that if we have an obstacle that simply invalidates some nodes and edges, and the way we encode this into our POMDP formulation, this is not a natural analog to an obstacle, is by adding a penalty term to our reward function. And this initially made me a little nervous because in general, adding this type of penalty term does not guarantee feasibility. But in the paper, we proved that in this particular case, under some mild conditions, that the optimal policy will not execute an infeasible action. The mildest of them is that if it's possible to reach the goal with a non-zero probability, which I think is true in all interesting problems. So if you visualize that lattice on an actual manipulator, it looks something like this. Green is reachable from the start configuration, gray and red are not. Here there's a scallop from the robot not being able to reach its elbow over the model plane. So now we have a sort of principled discrete model for robot kinematics that we can put into our POMDP, and the challenge becomes how do we plan efficiently? And really it goes back to this idea that we can track the state in both a hand relative and the full state space at once. So if you think about a hand relative space, it's essentially the full space with no obstacles. So the intuition might be that the value function of the optimal hand relative policy is greater than a value function of an optimal full policy. And we prove that in the paper. So this optimal value function is an upper bound on this, which gives us a heuristic we can use to guide our search. And in fact, in practice, we could do a little bit more than that. If we use the concept of a rollout policy from the online POMDP planning community, we can actually use the same heuristic we use as this upper bound as the value function we're greedy with respect to for our lower bound. And the intuition here is that if there is indeed no kinematic constraints and this value function is indeed the optimal hand relative value function, then this bound is tight and the online planner essentially just greedily follows the heuristic. The place where it deviates is if you have an active kinematic constraint. So it's a nice combination of combining offline and online planning to get efficiency. So in practice, we use these upper and lower bounds in Despot, an online planning algorithm developed by David Sue's group, which I think you heard about a very interesting extension to earlier in the conference. The general idea is we're going to do a tree search where we propagate samples through the tree and we guide the exploration of where we propagate samples based on these upper and lower bounds. Essentially, we try to minimize the gap between them and choose observations sort of optimistically. So The end result of this is we get one action, we execute this one action, we repeat the search in a receding horizon manner, and we're sort of incrementally exploring this high-dimensional joint robot object configuration space. And the power of this really shows if you look at the set of states that we explore. So this is the full lattice I showed you earlier, but if we only lazily construct the portion of the lattice that we visit, it's only this small portion for a particular time step. So we only have to collision check and motion plan for this small set of edges. And of course, you could reuse them between time steps. So the end result is that the type of policy it produces looks something like this. Just as before, the robot is able to force the object into a fingertip to localize it. Unlike before, you'll see that when it was about to hit that plane, it reversed direction and chose to localize the object with its other fingertip before it completes centering it in this green goal region. So I'll let that run for a second. Do note that I'll come back to this in the dirty laundry slide, but this is not playing in real time. So it does successfully complete the task. We did a fairly extensive evaluation of this in simulation. I don't have time to go into all the details here, but sort of the takeaway is that we compared it to a baseline that considers uncertainty but not kinematic constraints, and a baseline that considers kinematic constraints but not uncertainty. And you can find problems where each of those is optimal, but you can also find problems like this one here, where both of them perform significantly worse than an approach that considers both kinematic constraints and uncertainty jointly. So to conclude, just to go through some of the dirty laundry, as I mentioned earlier, this is not at a point where you can run it in real time. Depending upon how tight those heuristics are, 200 microseconds to 2.4 seconds. We have to discretize a few things to make this work, and we don't currently resolve kinematic redundancy. And I think there were some great ideas about how to address this at this conference and previously, and I'd love to talk offline if you're interested.
Thank you, Michael. Thank you, Michael. First respondent goes to Mark Mull.
I think it's great work. So you showed at some point that you had a very small exploration of the space, right? It seems to suggest, well, maybe you can.
Thank you. Maybe you can actually solve this with continuous POMDP solvers. Do you think that's practical, or is that still a ways off? I mean, you mentioned like real-time performance as sort of a concern, but it seems that maybe there's still room for trying this out.
I think that's a fantastic question, and one of the things I wish I could have done in this work. I think there's two aspects of that. For continuous state space, I think it's absolutely possible. Despot actually already works on continuous state spaces. The key limitation is getting a transition and observation model that's fast enough to evaluate. In my experience, this discrete model is around 10 to the 7th times faster than the fastest continuous model I could find. For continuous actions, I think that's a little bit trickier. I think there's some promising work like GPS ABT that might get us there, but I think it's still a very open area of research.
Thank you.
Good. One more question while we're getting set up? We're running a little behind, so we might use this opportunity to catch up. So let's thank Michael again. Thank you. And